All right, welcome back, everybody. So we're finishing up section 2.2 today. I'd like to finish it up. I haven't decided whether we want to just keep moving forward or going to do a work day tomorrow. The only thing is, in my notes, we have to do a quiz by next Friday, and over limits, and we have to get through section 2.4 for that. So we have to go through sections 2.2 through 2.4 and then have a quiz next Friday. So we're going to see where we're at. So we were talking about limits, right? And we said a limit, basically, the definition of a limit is as we approach a number, as we make x go to a number. Yes, sir. Are you recording? Yes, I am. As we make x go to a number, what happens to the output of the function, right? And we talked about, sometimes when the function is defined at that value, we could just plug it in. Like that whole x squared minus x plus 2 thing, we could just plug in 2 to see where the function is going to go. But we can't always do that. Like we saw here, we can't just plug in 1. We can't just say, okay, if I plug in 1, what's the function going to go to? So we've got to figure out ways around that. Because the function doesn't necessarily need to even be defined to be able to calculate the limit around it. Remember, the idea of a limit is the fact that we want to figure out what's going on around the function, not necessarily at that function, at the value of that function. The goal is to figure out what's going on around that function, or at that value, not necessarily what's happening at that value. I don't really care about what's going on at it, just around it. So we have this idea of not only checking from one side but the other. Remember, we were saying, okay, we're going to plug and chug from one side, plug and chug from the other side, just see, okay, we get sufficiently close to a number, and then we assume that that's going to reach that number, right? But what happens if I'm only able to calculate it from one side? What happens when I'm only able to calculate it from the left side or just from the right side? Meaning, what happens if I take an x value bigger than that number and start calculating down toward it? And I'm not able to calculate what's happening on the left side of it. What happens then? Well, what we can do is calculate one-sided limits. Examples 4 and 5 illustrate some of the pitfalls of guessing a value of a limit. It's easy to guess the value wrong. Oh, I think I need to go here. There we go, one-sided limits. This is a really weird function. I remember this from back in my calculus days. And yes, I do. Did I show you guys this? I still have my calc book, but not only my calc book, I still have my calc notebook. Oh, I think I do. It's somewhere on this shelf. I still have my notebook from when I took calculus. I kept the same notebook from calc 1 to calc 4, just so it was all in one spot. I looked it up. We did do the same example back when I took my calculus class. This is called the Heavyset function. I always thought that was really weird. I always thought it was like Heavyset. That's just a guy's name, and it'll talk a little bit more. The Heavyset. That's why it's capitalized. I was like, Heavyset? Like really? No, that's this guy's name. His name was Oliver Heavyset. Okay. But basically, the Heavyset function, it's used in like currents, like electrical currents, because either you flick on a light switch, either it's on or it's off, right? There's no in between. So basically, this function is saying, okay, at time 0, the light switch gets turned on. So they're saying 0 is off. The output of 0 is off, the output of 1 is on. So they say, okay, at time 0, the light switch gets turned on, and then at that point forward, the light is on. Okay? Think about this. Take a look at the function and say, okay, what is the limit of this function as it approaches 0 from the negative direction? From the left side of this function. As I get closer and closer to 0, where does this function equal? 0, right? As I get closer, say, what's the value of -1? 0. What's the value of -0.5? 0. -0.25? 0. -0.1? 0. 0. 0. 0. So I can say the value of that function, the limit of that function from the left side is 0. What about going from the positive end? Well, what's the value of the function at 1? 1. What's the value of the function at 0.5? 1. What's the value of the function at 0.25? What's the value of the function at 0.1? 0.0001, 0.0001. It's all 1. So the value of the limit going from the right side is at 1. So I have this idea of not being about being able to calculate the limit from either side, but them not being equivalent to one another. Okay? The right side limit does not match the left side limit. And this happens when there's these things called discontinuities within graphs. When one of the limits does not actually equal the other of the limit. What we can do is talk about it them being one-sided limits. When they don't match up, you can actually say, okay, I've got the left side limit, I've got the right side limit. Okay, so a little bit background on this guy. This function is named after the electrical engineer Oliver Heavyset and can be used to describe an electrical current with switch on, right? As t approaches 0 from the left, the function approaches 0. As t approaches from the right, the function approaches 1. So therefore, there is no single number that h of t approaches at time 0. Like, I can't say that it approaches one thing, because from the left side, it approaches 1. From the right side, it approaches 0. This is kind of like that sine graph that we saw get really weird right at the axis, right? Where the limit did not exist in the middle there. This is another example where the limit as t approaches 0 does not exist for this function, because the left side limit is not the same as the right side limit, okay? And here's our formal definition. This is our definition of one-sided limit. The notation that we use to say that it's coming from the left is to put a little negative sign as almost like an exponent type thing, yeah? Don't think of it as a negative exponent, but that's where it goes. That's where it's like a minus sign up as like a superscript, okay? So this notation is saying the limit as x approaches a from the left of the function equals a certain number. To say that it approaches from the right, we would just replace that minus sign with a plus sign, okay? If I put a minus sign as a superscript, that is saying approach from the left. If I put a plus sign, that's saying approach from the right. If I don't put anything, I say I am approaching from both the left and the right, because that is noting the full limit. If I don't put anything, that's noting the full limit from the left side and the right side. If I put a minus sign, it's only approaching from the negative direction. And I say the negative direction, but that's from the left direction. If I put a plus sign, that's saying approaching from the bigger direction, from the positive direction. Okay, that's how we note it. Okay, that superscript. Taking a look here. This is an example of coming from the left, coming from the right. This function. If I say I want the limit as x approaches a from the left, I'm basically like saying, okay, I don't care what's happening on the right side. That's why this graph is chopped off. I don't care about what the curve is doing on the right side of it. All I care about is what the curve is doing on the left side of it. And what does it approach? And it doesn't even need to be defined, right? The Heavyset function, there was an open circle at time 0 because it turned on at 1, right? And we didn't care that it wasn't defined at 0. We don't care what happens at that moment. We care what happens around it. So the limit as x approaches a from the negative direction is this value L, the output L. Likewise, this is what it would look like if I was only focusing on the right side limit. The limit as x approaches a from the positive direction. From the right side, I would be saying, okay, where's the function going? Where's it going? Where's it going? Where's it going? Where's it going? And at that moment, I can say, okay, the limit as x approaches a from the positive direction of this function is L. Now, the only time you can say that the limit truly exists is if these two things match each other. The only time these two you can say the limit truly exists at that value is when these two match each other. And this is a very important statement down here. The limit as x approaches a of a function, notice that I don't put a superscript there, right? I leave it blank, so I'm saying, okay, the full limit of this function at point A is L, if and only if, biconditional statement there, if and only if The left side limit and the right side limit both are equivalent to the same number. If this is not true, then this does not exist, okay? If the left side limit does not match the right side limit, say the left side limit was 5 and the right side limit was 7, I don't know, then the limit does not exist. For the limit to exist at a certain value, these things must be true. The left side limit must be a number, the right side limit must be that same number, okay? Okay, so let's take a look here. The graph of the function g is shown. Use it to state the values if they exist. Okay, what is this notation reading? That notation is reading, I want the limit as x goes to 2 from where? From where? From the left. Good. So I'm going to follow along with my function, and I'm going to say from the left side, what's the limit as it goes to 2? Well, what's the limit as it goes as x equals 2 from the left? 3. Okay. Do I care that the function does not equal 3? Or does not equal at 2 does not equal 3? No, I don't care what's happening at that moment. I care what's happening around it. I care what it's going to. Okay. What's the limit as x approaches 2 from the positive direction? So I go here. I say, okay, no. Get closer to 2. What's it going to go? What's the y value going to be? 1. So what can I say about the full limit? What can I say about the full limit? What can I say? Well, if it's left side 3, right side 1, do those things match? It does not exist. Okay? And you can always abbreviate DNE as does not exist. Okay? For the limit to exist, these things must match each other. And since they do not, the limit does not exist. Okay, let's do that again. What's the limit as x goes to 5 from the negative direction? Okay. X value 5. No. What's the value? Looks like 2, right? What's the value from the positive direction? Going toward 5. No. Looks like 2, right? Now, what does that tell me about the limit as x approaches 5 of g of x? What does it equal? 2. But you may be thinking, well, wait a sec. The function doesn't equal 2 at 5. That's okay. Remember, I don't care what's happening at that point. I care what's happening around it. So even though there's that discontinuity there, even though I've pulled that point out and put it somewhere else, I don't care what happens at g of 5. I care what happens around g of 5. And if the limit is g of 5, the limit as x goes to 5 from the negative of g of x is 2, and the limit as x approaches 5 from the positive of g of x is 2, then the full limit as x approaches 5 of g of x is 2. That make sense? You'll have a lot of these types of questions on your homework, where they'll give you a graph and say, okay, what's the limit here, what's the limit here, from positive, from negative, does it do this, and so on. Okay. All right, so let's take a look at this example. Let's investigate 1 over x squared. And then let's find the limit as x approaches 0 of 1 over x squared. First off, can I just plug in 0? No, because if I plug in 0, it'd be 1 over 0 squared, and that'd be 1 over 0, and that's no good. So let's see what's happening from the left side. Okay, because that's like our only method right now, right? That's the only thing that we know how to do, is we just plug and chug. Okay. I'm going toward 0. So maybe I say 1 divided by, and then I'll do, let's say -1. Let's go big and say -1 squared, right? Okay, we got 1. What if I plug in the same thing, but instead of -1, let's do -0.5. 4. Okay, let's see what's going to happen here. -0.1. Whoa, that escalated quickly. What about negative 0.01? Whoa. What about insert a 0? Okay. What's happening here? It's getting really big, right? Is it converging to one number? No. It's converging to infinity. It's converging to infinity. Does the same thing happening from the positive, is the same thing happening from the positive direction? Yeah, because what's going to happen when I square a negative, just like a square positive, it's going to be the same number, right? So I can say that 1 over negative 0.1 squared is the same thing as 1 over positive 0.1 squared, right? So no matter what, it's actually going to just keep getting bigger and bigger and bigger and bigger and bigger. This is what's called an infinite limit. This is what's called an infinite limit. We say that the limit as x goes to 0 of 1 over x squared is positive infinity. And yes, you have to be specific when you say positive infinity or negative infinity. Take a look at the graph. You see how it goes up? Then the limit goes to positive infinity. If that had been flipped downward, then you would say the limit goes to negative infinity. So be careful. Use the correct notation there. This is going to go up. This is going to keep getting bigger and bigger and bigger in my y values. This is going to look like a vertical asymptote. Graphically, infinite limits look like vertical asymptotes. Yeah.
It'll never go to both, will it?
Well, funny you ask, because you could have something that looks like this. Like just 1 over x.
I'm going to take the test.
Yeah, you could have something like this. Now, what's the left side limit? Negative infinity. What's the right side limit? Positive infinity. What's the full limit? It doesn't exist. Right. The left side limit would not match the right. You have calculated?
Yeah.
Okay. The left, you can sit right on it.
Perfect.
The left side limit does not match the right side limit, so therefore the limit would not exist. So I guess you could say that it does go to both, but you just have to specify left side to right side. And I think I get to that in a little bit too. So this is the intuitive definition of an infinite limit. Basically saying that if we let f be a function defined on both sides of a, except possibly at a itself, remember we don't care what's defined. We don't really care what's happening at a, is that if it keeps going bigger and bigger and bigger, or smaller and smaller and smaller, the limit of x, the limit as x approaches a of f of x is going to be equal to infinity. Okay. Again, this is going to graphically look like a vertical asymptote. Okay. We kind of have already talked about this way back in algebra 2. Guys, think about this. Remember the whole end behavior dance? We said, okay, positive, even, right? We used that really funky notation and we said as x goes to infinity, meaning on the right side, the function goes to infinity. Guys, we were doing limits. We were doing limits at that point. We just didn't understand what we were doing at that point. End behavior is all limits. It's saying as you go to smaller, it's going to go up or it's going to go down. We were talking about infinite limits. We just didn't realize we were doing it at that point. This notation is just the same thing. It could go down rather than could go up. Let me talk about this. For a minute, I thought that was the bell. Let me talk about this diagram here. I mean, it was a bell. Let's take a look at these graphs down below here. Take a look. The limit as x approaches, I know the font is small. The limit as x approaches a from the negative side. From the left side. What's the limit? Positive infinity. Goes up. Positive infinity. The limit as x approaches a of f of x from the right side. Positive infinity. The limit as x approaches a from the negative side. Going down. Elevator down. Negative infinity. From the right side, negative infinity. So it's that idea of a vertical asymptote. If you see a vertical asymptote, there is an infinite limit at that vertical asymptote. That's why we spent some time talking about how to identify vertical asymptotes. So all in total, this is just kind of like summarizing everything that we learned over the past couple slides. The vertical line x equals a is a vertical asymptote of the curve if at least one of these statements is true. See, we talked at great length in Algebra 2 about vertical asymptotes, but we didn't really understand why they were vertical asymptotes. We didn't understand why they were vertical asymptotes. Now we can truly understand why. We can say that the limit as x goes to that number, that vertical asymptote number, the function will either grow rapidly or decrease rapidly to infinity. And either of these things must be true, or both. Remember, the reason this is true is because these two things are true. From the left side it goes up, from the right side it goes up. And if they both go up, then the full limit goes up at that number too. That means it's matching on both sides, like our example. On the left side it can go down, on the right side it can go down, and if they go down on both sides, then it's there as well. But again, they don't need both of these. You don't need both of these. That's what we were talking about in that weird graph of the just 1 over x, right? That's a vertical asymptote. From the left side at 0, it goes up. From the right side of 0, it goes down. So really, this diagram is showing you this and this, right? From the right side, it goes up. From the left side, at 0, it goes down. Okay? Let's take a look here. Let's take a look at 2x over x minus 3. Wouldn't you agree that from the look of the equation, there's a vertical asymptote at 3? This is why we spent so long looking at rational functions and seeing where it's undefined, seeing where the vertical asymptotes are. The vertical asymptote here is at 3. Can I plug in 3? No, I cannot. If there is a vertical asymptote, that must mean the limit must either go to infinity or negative infinity. So let's see what's going to happen. Am I just going to look at the graph? Yeah, I was just going to look at the graph. So let's take a look at the graph. Let me get my stats out of there. Let me turn my plot off. And let's say, okay, 2x divided by x minus 3. Zoom 6. Okay, come on. Come on. Hello? Hello? McFly? No? Whatever. On the left, let's answer this question first. On the right side, hey, just needed a minute. I had to talk to it. On the right side, we all see the vertical asymptote. What is the limit as x approaches 3 from the positive? Positive or negative infinity? Positive infinity. As I go on the right side, the limit as x goes to 3 from the positive direction of 2x over x minus 3 should be positive. If you want to just like reinforce that, write a plus that, that's totally fine. If you don't write anything, I assume you're talking about positive infinity. The limit as x goes to 3 from the negative. What is that? Negative infinity. You see that? That's how that works. That's the notation behind it as well. That's how we read that. And I believe that's the exact same thing that we drew. Have to go over that. Okay? So let's take a look here. Find the vertical asymptotes of tangent of x. Find the vertical asymptotes. Now, when I go to find the vertical asymptotes, remember, I'm looking to see where the function is undefined, right? I'm looking to see where the function is undefined. Guys, what is tangent equivalent to? If f of x is equal to tangent of x, is it tangent sine over cosine y over x, right? Tangent of x is equal to sine over cosine. Okay, where is this function undefined then? Whenever cosine of x equals what? Equals 0. What values along the unit circle give us an x value of 0? We'll think about the unit circle. Ooh, that's a pretty good circle. What values, what angles give me the x value of 0? So it's got to be one of the axis points, right? Is it going to be 0 and pi, or is it going to be pi over 2 and 3 pi over 2? Pi over 2. Pi over 2 and 3 pi over 2. X value, now y value. So I know x is going to be equal to pi over 2 or 3 pi over 2. Right? And notice how I leave room. Plus all rotations of 2 pi n, where n is an integer. Take a look at what it looks like graphically. Why are these things happening? Why are there asymptotes there? Well, because at each piece, at each value, on the left side, it's going to grow. On the right side, it's going to decrease. Right? So the left side limit at pi over 2 is infinity, where the right side limit of pi over 2 would be negative infinity. Do I care that they don't match? No. Because remember that table, just one of them had to be true to be a vertical asymptote. Okay, just one of them had to be true to be a vertical asymptote. So at negative pi over 2, the right side limit's negative infinity, the left side limit's positive infinity. And that will keep going in each iteration of 2 pi, right? That keeps happening. Last thing here, when else do we have vertical asymptotes? We also have vertical asymptotes when we talk about logarithms. Okay, that's the last place where we see vertical asymptotes. We see vertical asymptotes in tangent, in rational functions, and also in logarithmic functions. That's the only, really, I don't want to say the only places, but that's most of the times where we see vertical asymptotes. So take, for example, ln of x, log base e of x. If I graph ln of x, this is what it looks like down below here. If I graph ln of x, do you notice how on the right side, as I approach from the right side, as I approach 0, it keeps getting smaller and smaller and smaller and smaller. It will go down to negative infinity. Is the function even defined on the left side of 0? No. Negative values of x do not make sense. Negative values of x are not real. Okay? So I don't even care that it's undefined on the other side. All I care about is that on the right side of it, it will go down to negative infinity. Is that true for all logarithmic functions? Yes. There will be a vertical asymptote for all logarithmic functions. Yes. Even if we shift it off the axis. You know, what will do that? Well, remember that an ln of an x plus 2 shifts that to the left 2 units, right? So that means my asymptote is no longer at 0, but it's at negative 2. So we can say at ln of x plus 2, the limit as x goes to negative 2 of ln of x plus 2 is negative infinity. Right? So wherever that asymptote got pushed to, that's where the limit will go to infinity. Or excuse me, negative infinity. For example, if I had made that the, log base 3 of x minus 7. Log base 3 of x minus 7. What's the shift on that? Left or right? Right 7. So that means that the limit as x goes to 7, positive 7, and I guess I should have specified. I should say on the right side of that. I should put a little plus sign here because does the limit exist on the other side? No. So as the limit as x approaches 7 from the positive direction of log base 3 of x minus 7, we would say that still goes down. No matter what base I choose, it's still going to go down infinitely. Okay. So where do vertical asymptotes happen? They happen at logarithmic functions, they happen in rational functions, and they happen in tangents. Okay? That's where they happen. And the reason that they happen is because of infinite limits. Yes?
If it were to ask you what would be the limit of x to the 0 but with a negative sign, would that just be do not exist?
Does not exist.
Okay, so if there's nothing on that side, you just put it doesn't exist.
Right.
Okay.
Yeah. Because the function doesn't exist on that side either.
Okay.
And we would say that the full limit, that's why I had to note this, the plus sign here. We would say that the full limit does not exist either.
Okay. Because it only exists on the positive side.
Because it only exists on one side.
Right.
Okay, that's it for the notes for today. You got about 17 minutes to work on your homework.